It was unfortunate today that we got disturbed. Um, I wanted us to cover what is called exponential functions and then logarithmic functions. So this lesson will be based on those two functions. Let me just write it down. So I want us to talk about exponential functions and logarithmic functions. So that's the main purpose of today's lesson. So, what are exponential functions? First of all, let's start with f of x. Let's say f of x is equal to x to the exponent a there. And this one, we said that this is an independent variable. And then this one here is a constant. So this one is a real number, which is a constant, and this one, which is a base, is an independent variable. We said that functions of this kind, and we gave them a name, and then we said that these functions are called power functions. I am trying to include power functions here because usually students, they usually confuse power functions and exponential functions. Now, what are exponential functions? Exponential functions are functions of this kind, but now we are switching the base and the exponent. So as long as a function is a to the power x, then this function is a exponential function. This one now is an independent variable. And then this base here is a positive real number. So exponential functions are functions of this kind, which is just reversing what power functions are actually doing. Now let us take a quick analysis of this. We said that for the exponential functions, our a is greater than 0. So if a is greater than 0, which means that whenever we have a, we are allowed to have any exponent d. We can have negative exponents, we can have positive exponents, and we can actually have 0. Now, since a is greater than 0, and we are plugging in a 0 here, we can see that this one is always going to be equal to 1 when we apply laws of exponents. So this is always going to be the case, and it's always going to be defined, which means that all the exponential functions, all exponential functions have a y-intercept. Have a y-intercept at x is equal to 0, and that value is going to be 1. That's what I'm trying to say here. So we have a y-intercept at x is equal to 0, and that y-intercept is equal to 1. So all these exponential functions will intersect at that point 0 is to 1. So all of them will pass through at that point. Now, can we analyze different cases here and see what is the shape of that? Because all the functions we've studied so far, they all revolve around, I want you to understand the shape, I want you to understand the domain, I want you to understand the range, I want you to tell me if this function is even or is this function odd function. So those are the things that I'm actually looking for when it comes to these functions, these basic functions. We talked about sine, we talked about cos, we talked about tan function. So at least when we're talking about those functions, power functions, rational functions, just try and get the basics of what is a domain and all those things. Now, for this one here, first of all, we have this f of x, and this f of x is a to the power x. But now, I want us to have the first case whereby we're dealing with a is greater than 1. So we're getting a value that is greater than a 1 here. What are the shapes of these particular functions and how they look like? And how can we compare them? Okay. Let me do this. So, the first thing that we said is that all these functions will pass. Let me make my 1 here so that this becomes clear. So all these functions will pass through this point, that is our 1 there. And now that we have that, I am going to move this a little bit down. Want to move it a little bit down so that this function here is a little bit cleaner, right? And a little bit, want to make it a little bit tall, something of this nature. And then on top of that, I'm gonna have this, and then on top of that, I'm gonna say these are y-axis and these ones are x-axis. So first of all, I am going to pick some values here. I'm gonna place this to be 1, 2, 3, 4, and then this side I have -1, -2, -3, -4. So we're gonna have 1, 2, 3, 4, and a 0 there. And then here we're gonna have -1, -2, -3, -4. Now, of course, we are trying to plot our f of x is equal to a to the power x here. So the goal first, we want to deal when a is greater than 1. So let's pick first a is equal to 2, a is equal to 3, a is equal to 4, and actually analyze what happens as a keeps increasing, right? So we're gonna start with f of x is equal to is equal to 2 to the power x here, and then we can try and analyze. If I am placing a -4 when at the value of x, what will I get there? I will get f of -4 is going to be 2 to the power -4, which is the same as 1 over 2 to the power 4, which is the same as 1 divided, this is 2 times 2, which is 4 times 2, which is 8 times 2, which is 16. So we're gonna have a 16 there, 1 over a 16. So I'm gonna say 1 over 16 is somewhere there. I'm trying not to be precise, but to give you a clear image of what is actually going on there. And then if I pick a different value there and say we're at x is equal to -3, so we're going to get f of -3 is equal to 2 to the power -3, which is equal to 1 over 2 to the power 3, which is the same as 1 over 2 times 2 is 4 times 2 is 8. So we have 8. Between 1 over 8 and 1 over 16, you choose which number is bigger. Since this number is bigger than 8, then this fraction have to be smaller than 1 over 8. So this one is a little bit above compared to the previous point. And now again, we pick a different point here. And our point now is going to be f of -2, which is going to be 2 to the power -2, which is the same as 1 over 2 squared. 2 times 2 is 4, so it's 1 over 4. So our 1 over 4 is going to be a little bit above than the previous points. And if we are placing a -1, we're going to have f of -1, which is the same as 2 to the power -1, which is the same as 1 over 2, which is half. So this one will be a little bit above all these points there. And at 0, of course, we're going to be at 1. And then at 1, we're going to be somewhere there. I'm just going to say 2. So this curve of ours is going to pass through these points somewhere like something like this. I'm trying to be precise, so it's going to be like this. But no matter what I can do, if I plug in a value here, I will always gonna get a positive value here. There is no, if I'm placing a negative value here, I'm still a positive value, I'm gonna get 1 over a positive value. So since this is positive, it's gonna be 1 over positive, which is positive. Positive over positive is going to be positive. So here we always gonna go this particular direction here. And also to add to this, not only that all these exponential function will have a y-intercept at x is equal to 1, all these functions will have a horizontal asymptote at y is equal to 0. So what these functions will actually do, they will never touch the x-axis. So they keep going, but as if they are going down, but they will never actually touch the x-axis. So here you're gonna have y is equal to 2 to the power x. Now, what really happens if you have a to the power 3? So what basically will be different between these two curves is that a to the power 3 will be a little bit below than this, and it's gonna go all the way, and then when it meets there, it's gonna meet there and catches this function. But once it catches it up, it passes it and it becomes bigger than this function. So you're gonna have y3 to the power x, right? You can even test the other points and test this a when a is equal to 4. A to the power 4, 4 to the power x is gonna go down here, and then it's gonna go all the way, and it catches these two functions, and then it goes all the way up there. So this is y is equal to 4 to the power x. And of course, you can still track this by checking the points, and then it will give you a clear image. So as a increases, we are actually going closer and closer to the y-axis this side. And this side, we are actually going closer and closer to the x-axis. So that's what actually happens if you keep increasing a. So we have this nice thing that is here. Now, if we look into this curve, they can take all the values of x, looking into this function here, because I can plug in a value, a negative value here. I will get 1 over something, which is positive. And also, if I take a 0 here, I will get a 1. If I take a positive value, I get a very big number. So I can plug in any value here. So the domain of the exponential function, where a is greater than 1, x is the element of real numbers. That's the domain. But if you look into this function will never take the negative values. It will only gonna take the positive values. So the range of this a of x is going to be y is a set of all real numbers such that y is greater than, let me say greater than or equal to 0, and then we analyze. Because this function will never really touch the x-axis, in other words, they will never really be equal to 0, then we remove the equality there because they just have to be greater than 0. And this is under the case where a is greater than a 1. Now, we want to see what will happen if we have 0 less than a and a is less than a 1. We need to analyze those particular cases. And then, of course, for that, what we normally do is we do the same thing. We have, we're still looking at f of x is equal to a to the power x, but now 0 is less than a and a is less than a 1. So what will happen in that particular case? You draw a line again, a vertical line. We'll draw it like this. And now that you have this nice vertical line here, let's try and draw a horizontal line here. And we say that we have the y-axis this side, we have the x-axis that side. And then of course we try and pick some points as we did in the previous case there. We pick some points here. Now what will really happen here is this. I want to pick a value in between 0 and 1, and I will make sure that I keep, let's say I'm gonna start with 1 over a 5. A is equal to that, and then I will go with a is equal to 1 over a 4, and then I'm gonna go with a is equal to 1 over 3, and then a is equal to 1 over a 2, and then we analyze what happens. So I'm gonna just pick a couple of points. This is 1, this is 2, this is 3, this is 4, this is 1, this is 2, this is 3, this is 4. Of course this side is minus, 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 and you have a 0 there. And at this point here, I'm gonna say this is equal to 1 because all the exponential function have to pass through 1. And also another thing is, along the x-axis, the x-axis act as a horizontal asymptote of these particular functions here. I am going to start with this one here, right? So if let's say I have that, I want to find out what is f of let's say I have 1 over 5 to the power x. If I am plugging in here a minus 4, what will I get? I will get 1 over a 5 and raised to a minus 4, which is same as 1 divided by 1 over 5 to the power 4. And having a power outside of a fraction, it just means that you have 1 to the power 4 and 5 to the power 4. And 1 to the power 4 is the same as 1. And we change this division to multiplication. And now we end up having 1 times 5 to the power 4 over 1. So 5 to the power 4 is going to be 5 times 5 times 5 times 5. So we have 5 times 5 is 25. Or I can just have this. 5 times 5 times 5 times 5. So we get our 600 and something, which is a very, very, very big number that is somewhere up there. And then if we plug in minus 3, so you're going to have 1 over 5, and then you raise it to the exponent minus 3, so you're gonna get 125. 125 is a little bit below, actually way too below, so I can just say somewhere there. So this one is 625, this is 125, and then next we just look at minus 2. What's going to happen if we have a minus 2? Then we have a 25. 25 is way too below. I'm just estimating here. And then if I'm plugging in here a minus a 1. So we end up having some 5 there. So we'll end up having some 5 somewhere there. And then when this is equal to 0, of course, we're going to get a 1. And then we get a 1 there. We're going to get 1 over 5, a number that is, let's just say somewhere there. You can see that this is gonna go all this way like this, and then it comes down, and then it comes down, and then it comes down all the way like this, and then it keeps going there. So I have this. Now if I am increasing this function here, what will basically happen here? I can just say I'm gonna test two values. I'm gonna test 4 there, and then I'm gonna place a minus 4 there and see. So I'm getting a value that is below this, that is somewhere there. And then I'm gonna test another value there, and then I'm placing a minus 3 there. I'm getting a 64, which is way below that 125. And then I'm getting a minus 1. For a minus 1, I will get a 4, which is also below. And if I'm placing now a1, right, now I'm gonna place, let me say a 2. What will happen? I'll get a 1 over 16, so which is above. So this function here will just come all the way like this, come all the way like this, and then it meets at 1, and then it goes all the way down there. And what this is actually saying, this side, is that, remember that this one is smaller than this number. So when you are moving from this, it goes down, it keeps going down closer to the x-axis, as we're actually doing with that one, with the one that we did above. And so the next one will be this one going all the way and meets there, and then it's like this. And then the next one will keep trying to try and move something like this. So this one is going to be, we have 4 here, 1 2 3 4. So this is going to be this is going to be f of x is equal to 1 over 2 to the power x. This one is going to be f of x is equal to 1 over 3 to the power x. This one is going to be 1 over 4 to the power x, and this one is going to be 1 over 5 to the power x. So as this value of a keep increasing but still less than 1, this one keeps going, this function keeps going down to approach the x-axis. But while this side, these functions, they keep going up because they want to approach the y-axis, just like in this particular case over here. So what is the domain? The domain is still the same as in the above case, and the range is still the same because this function will not really get to the x-axis, will not actually touch the x-axis. I'm trying to give you a real picture of how this thing actually is going to look like when it is cleaner. I'm trying to see if is it possible for us to see a cleaner image of what is basically happening here. If it is possible, I will see, because as I keep drawing this, it doesn't look that much clean. Let me bring this one here. What is basically happening here, as I've just said now, just to give you a little picture. If you look at, I'm gonna try and increase this, yes, just that we can see the functions here. I hope you can also see. At this point here, you have y is equal to 2 to the power x. So it passes at 1, this blue curve, and then as you increase this value to 3, we get a value that is getting closer to the y-axis. And if you increase this 3 to a 4, then you get 4 to the power x. It gets closer. So as you keep increasing this number here, we are getting a value that we are getting a curve that is little bit closer to the y-axis as we keep increasing this. And if you look at y to the y is equal to 20 to the power x, it is very close to the y-axis compared to this, because this 20 is bigger than all of them. But this side, as this is pushed to close to the y-axis, it is actually bending towards the x-axis down there. And if you look into this one, which was the second closer to the y-axis, and this side is getting closer and closer to the x-axis. So we have that mixture of these things trying to bend. They are trying to bend towards the y-axis, compared as you keep increasing this this value of a. And if you look into this side, looking into these fractions here, 1 over 20 is less than 1 over 9, and 1 over 9 is less than 1 over 6, and 1 over 6 is less than 1 over 4, and 1 over 3 is less than 1 over 2. So as you keep increasing these values, you can see that this one is getting away and away to the y-axis. In other words, it keeps getting a little bit closer to the x-axis there, so it's getting this side and that side. But if you look into this side, the one that was closer to the y-axis, it is the one that is closer to the x-axis this side. The one that was getting very, very, very away from the y-axis, it is actually way too above than the x-axis. As you can see that these things are trying by all means to try and make sure that if we can keep increasing these, keep increasing them until we arrive at 1 or until we arrive at 2, we can start seeing that this function will go like this, go like this, go like that, until we start to have things that are going this way. So that's what will actually happen. So these one are trying to get closer to this side, while this side is trying to get closer to the x-axis. So this is how this these curves looks like when it comes to the plotting, and also this is how these curves look like when it comes to the plotting. Now we have talked about these exponential functions, and we said that this is not a nice looking thing, and we said that we have a nice thing like this. If a is greater than a 1, this is y, this is x. So we end up, in a nutshell, we have a shape like this. This is f of x is equal to a to the power x, where a is greater than 1. Now, if you have this nice curve here, the question will be, is this an even function or an odd function? Note that if you have an even function, you must have a mirror there. One mirror along the y-axis, so these y-axes are a mirror. If you were to stand here and look into this mirror here, what would you see? How would this graph be seen in the mirror? So just taking this point here and going all this side, how would we be able to see the image of this on this mirror? It would be something of this kind here. Would be something of this kind. But if you look into this thing here, this piece, this green piece here is not that piece there. Therefore, this exponential function is not an even function. Not an even function. Now, if again I were to plot a different plot and say, suppose I have a function which is f of x is equal to a of x, where a is between 0 and 1. So this is going to be the plot. Now I'm going to take an orange color and look at this. This is the mirror along the y-axis, and I'm going to look into this side here. If I were to stand somewhere here, what will be the image of this portion here in the mirror? The image of this, or what will you see on the mirror, it will be this curve here. So you will end up seeing this curve here. But looking at this orange piece here is not the same as this remaining piece. So you cannot get this remaining piece by reflecting this along the y-axis. Therefore, even in this case, this exponential function is not an even function. Right. Now that we have done with the even function, we know that this is not an even function. We need to check, is it odd then? Because just because a function is not an even function, or it doesn't have an even symmetry, it does not necessarily mean that it is an odd function. It's possible that you have a function that has an even, it doesn't have an even symmetry, and also it doesn't have an odd symmetry, which is a different case. So we want to check if this is not one of those cases. Now, when you are dealing with odd, you have two mirrors. One is along the y-axis, and the second one is along the this is the second mirror along the x-axis. Now, if I were to look into this, we have two curves here. Suppose now I look into this portion here, along this mirror, I will get something of this kind. And then if I look into this portion into the mirror, I will get that. Now let's just look into one function here. One. And let's look into this curve alone. So if I were to look into this point all the way up there, what will be the first image along the y-axis? The first image, when you look into this mirror, it will be this curve here. Right. When I'm looking at the second mirror, so I'm standing here, looking into this image here, this point here will be a point there. And this is going that way, so it will start going something like that. Right, trying to follow that pattern. But this portion here is not the same as that. So this function, this part, because we looked into this in the first mirror and we saw that it was that. And then we looked into this into the second mirror, which is the x-axis, we saw that it was going this way. Now that this was going this way, this portion here is not that portion there. So we can say that this one is not an odd function. Now, let's try and see if this one will be an odd function or not. If I look into this, let me use a different color here. I'm going to use a red. If I look into this piece alone, and I look into this mirror, what will be the image of this mirror there? The image of this mirror will be this piece over here. Now, I am standing here looking into this mirror. What would I see on this mirror? It will be this point here, will be this point there, and then this is going that way, so it will be going this way. But looking into this piece here is not the same as that piece, which means that this one also is not an odd function. It's not an odd function. So, in a nutshell, an exponential function is neither odd nor even function. So it doesn't have an odd symmetry or an even symmetry. So we are done with symmetry. We know the domain that it takes all the x values. We know the range that is always above the x-axis. Now, let us talk about something that is very important. We talked about the shape of this curve here. I'm going to draw two curves here, and then we start talking about this. I have a curve here. I have another curve there. And then I'm going to do this here, and then I'm going to do that there. This is going to be x, and then we have that, 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 and we have that, and then we have that, and then we have that, and then we have this, and then we have that. Now that we have this thing here, what is this gonna be? All these plots, this we want to plot f of x is equal to a to the power x, but this side we want a to be greater than a 0. This side we're gonna have f of x, which is equal to a to the power x, but here our a is ranging between 0 and 1. We said that in that case, if these are the y-axis, x-axis, y-axis, and x-axis, an exponential function under this case, where a is greater than 1, is going to pass through here, but it will be increasing throughout. And if it is a is ranging between 0 and 1, we're going to get a nice function that is decreasing throughout. A nice function, nice curve that is going all the way down, but it will never touch the x-axis. And this point is 1, and that point is 1. Now, what are we going to do here? I want us to create a mirror image along the line y is equal to x here. So this is y is equal to x, and then here I also want to do the same thing here. I create a mirror there at y is equal to x here. So if you look into this one here is our mirror. So our mirror is here, and here we have a mirror there, right? Because we have a mirror that is sitting there, if I were to stand in this point, where will I see this point be? Where will I see this point be? Remember, I don't want you to get confused here. The mirror here was there at this point, so when you're standing here, the image was supposed to be at that point of this point. But now, when you are standing here and the mirror is along the line y is equal to x, what is going on? You're standing here, you look into the mirror, the point, this point will be a point there. So you're gonna have this point there. This point will be along the x-axis. And again, if you're looking along this mirror here, you're standing there, you will see that this line here, in the mirror, when you're looking into it, this angle should be the same as that angle. So this line here will be the same as this line over there. Just gonna place it like this, which means that because the vertical asymptote was, the horizontal asymptote was this, so now we will end up having a vertical asymptote. What's going on here? So we're gonna end up having a vertical asymptote. So we had a horizontal asymptote, but this horizontal asymptote, when you look into the mirror, it will become a vertical asymptote. And this curve here was not touching the x-axis. This side, it will not be touching the y-axis. It will not be touching the y-axis here. This was getting closer and closer, and then it kept trying to get away. It's gonna do the same thing here. Get closer and closer, and it's gonna try and get away. So the reflection of this curve will be that curve, and the reflection of this curve is gonna be that curve. So this is the new curve. We'll talk about what is that, the function that is creating that curve there. The same thing this side. This was a horizontal asymptote, but when you look into the mirror, this angle should be the same. In other words, this line here will become this line there. So the x-axis will become the y-axis. The horizontal asymptote will become the vertical asymptote. So we have a vertical asymptote here. Asymptote. There is a p here, asymptote. So if this function here was not touching the x-axis, which means that it's supposed to not touch the y-axis. So basically what will happen here, this point will be that point there. And now what is it going to happen there? This function here is getting away from the mirror. It should be trying to get away from the mirror. What am I doing here? Okay, let us work this thing out. Now, what is basically happening here? This side is trying to get closer to this. Remember that this line will become this line here on the mirror. So what is this curve doing close to this line? Is trying to get as far away as possible. This line here, when this one goes and becomes here, this one will become that line there. So since this one is getting closer there, at this point here, it should be getting closer to that side, something of that sort. Right? I think it's just this diagram is not really drawn to scale, but let me try again so that we can see what is basically happening here. We have this point. This point is somewhere. This point should be somewhere there. I'm just gonna try and place it there so that we can meet this point. So we will try and keep getting closer and closer, and then this goes away like this. So it's going away this way. So this one here is this part here. That part that is going that way is that part that is going that way. So you are seeing this in the mirror to become something of that sort. Now, what is this function and what is that function here? Notice that at this point here, I'm going to use a red. At this point, x was 0 and y was 1. But at this point on the mirror, we had x was 1 and y was 0. The same thing happened here. We had 0, 1, and then here we had 1, 0. So what is basically happening here? We had a horizontal asymptote. We ended up having a vertical asymptote. This x-axis here became the y-axis in some sort. So basically what we did here, we interchanged x and y. This x here became a y there, and this y here became an x there. This horizontal asymptote became a vertical asymptote. So this curve here, since we had our f of x is equal to a to the power x in both of these functions, or let me just say y is equal to a to the power x. This curve here interchange x and y, so this curve is x is equal to a to the power y, and also in this particular case here, x is equal to a to the power y. So that's what this curve is. Because we are used to having y as the subject of the formula, we want to define a new function, the logarithmic functions. So we said we have x is equal to a to the power y. I want you to take note of this. This one here is an exponent. And this one here is the base. And this one here, I just want you to call it's a number. Right. So we have a number is equal to base equal to an exponent. So this is what we'll be using throughout from now on. Now, what is this function that we actually define? We define this function in such a way that it is the same function as this function here, but now y is the subject of the formula. So you're going to have your y is equal to y, which is an exponent, and then you're going to have log, which is a logarithmic function, a x. So we change this. So these two things are equivalent. In other words, we have now an exponent is equal to log base. The number is coming here. Right. Let's go back. So we have this nice function here. So in this curve here, which means that this function here is the same as, I'm going to rewrite it as y is equal to log ax. The same things go for this particular function here. I'm going to just rewrite it and just say we have y is equal to log ax. Now that we have log ax, what is the domain of this function here? This function is of that type or of that type there. Let us try and make it a little bit cleaner. Then it will be easy for us to analyze, because we want the domain of this particular function here. We want the domain and the range. So When a is greater than 1, we said we ended up with a nice function that is increasing if a is greater than 1. So we had a nice function that is going all this way like this. So this one is y is equal to log ax, and that point here is 1 when x is equal to 1. But this point here, I mean the y-axis, the y-axis become now a vertical asymptote for this function, asymptote for this particular function here. Now, what is a domain of this function? Remember that this one here is when a is greater than 1. And if a is less than 1, we get a nice thing, a nice function that is going all the way, cuts 1, and then it goes that way. So this one, you're going to have y is equal to log ax. But now, our a is ranging between 0 and 1. So it looks like this. But what is the domain of this function? The domain of this function, the log a of x. You can see from this curve that we can plug everything that is positive, but when it comes to the negative side, it is not defined. So x is an element of real numbers such that x is greater than a 0. So we cannot plug in 0 because at 0 we have vertical asymptote. Right. Now that we have that, I want us to look at the range. The range of this log function x is going to be y is an element of real numbers, because it takes, if you look at the blue one, it takes all the values along the x and along the y. This is y, this is x. It takes all the possible output along the y-axis. So it is a set of all real numbers. And if you look into this one also, it takes all the possible y's along the y-axis. So it is the set of all real numbers. Another way to look into this is that when you were interchanging, we had a domain here of this function. The domain of this function was x is an element of real numbers. So when you have a mirror along the line y is equal to x, the domain becomes the range. So you just change the x there to be y is an element of real numbers, and the range becomes the domain. So x is going to be the element of real numbers such that x is greater than a 0. This is what has happened up to this far. So now that we have this, what are the laws of logarithmic functions? So we go to the laws of logarithms, or laws of logarithmic functions. And when you are actually doing that, I think I do have some nice pictures here to give you clarity on this. I'm gonna subtract a little bit so that you can see. When you're going through these notes, you will notice that there's some more information. As you can see here, I was trying to place a mirror there so that you can see this curve on the mirror, so it is cleaner there. And also here, when I was placing a mirror there, I want you to see this red curve in the mirror, that when I'm standing this side, this red thing here, it will become this portion here. And when I'm standing this side, looking at this portion here, which is red, is going to become that side there. So basically, that's what usually happens. So we look at the laws of logarithms, right? So let me put this aside. I think I've covered everything that we actually needed to cover in this. We talked about the domain and the range. Now the laws of logarithms are very simple. We have 1, we have 2, we have 3, we have 4. We're just gonna cover 4 of them. If I take log a of x and y, so the logarithm of the product of x and y, I'm supposed to get log a, remember this base is a, this base is a, of x, plus log a y. And if you take log a of x and y, you're supposed to get log a, and then the numerator is the one that goes first, and then you subtract log of a y. And if you take log a of x to the power b, this is the same as bringing this b down. You have b log a x. So that's what you get. And if you take log a x, you still get log b x, and then you divide by log b a. I want you to take note of this. I have introduced the number b here. This number can be anything as long as this number here is positive. And you can plug in any number. Then when you are dividing this value here and the base is here, you will actually get the same answer. Even if you decide to plug a 10 here or a 20 here, you're going to get the same answer there. Now, let's try and look at the proofs of these things. Proof. We're going to start with number 1. We wanted to prove that log a of xy is equal to log ax plus log a y. Now, how do you prove this whole thing here? This is very simple. You're just gonna say let capital letter X to be equal to log a x, and we'll let capital letter Y to be equal to log a y. Now, what I want you to notice is this. Whenever you have a number equal to a base raised to an exponent, this is equivalent to saying that I have an exponent equal to log base, the number goes there. So these two things are equivalent. So I want us to use this to actually prove that. So we're gonna say that, okay, if this is true, then this here, x, this is the base. We're gonna look, we have this now. The base goes there, the number is there. So the number here is x, so I have x, which is a number, and then I'm looking at, this is the number, I've got it. Now this is an exponent, this is the base. So I'm gonna take the base a, I have a to the exponent, so this capital letter X is going to be the exponent, and this implies that. And if I look into this, y is going to be the base raised to capital letter Y. Now let's look into this. If I go closer to this, I want to look x times y. I'm going to take x and multiply by y. So x times y, what am I going to get? I am going to get a to the power x times a to the power y. When multiplying powers of the same base, you add exponents. So this is the same as a to the power x plus capital letter y. So it's capital letter x and capital letter y. So we have, let me go down a little bit. So we have xy is equal to ax plus y. So we have this nice thing here. And if you look closely to this, this part is an exponent. I want to bring it down using that law again. So x plus y, this was supposed to be a capital letter Y, is equal to, now I have the exponent. I want to have a log there. So I'm going to have log, what is the base in this thing? I have a, what is the number? The number was xy. So I'm going to have xy there. If you go back to the beginning there, we said our x is the same as log ax and our y is log ay. So now we end up having log ax plus log ay is equal to log axy. And we have actually proved this, that log axy is the same as log ax plus log a y. Now let's try number 2. Number 2 wants us to prove this same thing, so we're gonna prove it using the same thing, same rule. So this is Roman figure 2 or number 2. Let me put it like that. Again, what we do is just say let capital letter to be equal to log a x and capital letter y to be the same as log a y. And then the next thing, we know that this is the same as, we use the same thing here, saying that if I have a number here is equal to a base raised to an exponent. This thing is equivalent to saying that I have an exponent is equal to log base the number, right? So I'm gonna convert this thing there, go back to green. So this means that here I am going to have x is equal to a to the capital letter x and small letter y is equal to a to the capital letter y. And of course, what I'm gonna do, I'm gonna divide x by y so that I can get a to the capital letter x and a to the capital letter y. When dividing powers of the same base, you subtract exponents, so you're gonna have a and then you're gonna have x minus a y. So we have, this is what is happening, this is what is happening. X over y is the same as a to the exponent x minus a y. So this is important. Now we take this and we convert it back to that format there. This is equivalent to saying I have an exponent which is x minus 1, which must be equal to log base, which is a, times the number, which is x over y. And then you replace this as the original thing as log ax, and you replace that as the original, which is log a y is equal to log a x over y. So we are done with number 2. It's not that hard. Now I want us to do the same thing to number 3. Number 3 was just saying that, can you prove that log a and then x to the power b is equal to b log a x? So what we're actually doing, this is small letter x. We have x. So here we look into this and then we just say let capital letter x to be equal to log a x. Again, our very first principle is that whenever we have let this to happen, and we know that if you have a number equal to a base raised to an exponent, this one is the same as having an exponent equal to log base a number, right? Now that we have this, we're gonna change this one. This means that now we're gonna have this. This one is a number, is going to be x equal to the base, which is a raised to an exponent x. So we have this nice thing that is there. What does that supposed to mean for us? It means that if I have x, which is this one here, x to the exponent b, this has to be the same as a to the power capital letter x all raised to b. I'm raising on both sides this to b. And now, when you are taking a power of a power, you just multiply the exponents there. So this is the same as a to the power b times x. So we have x to the exponent b is equal to a to the exponent bx. And then what you do here is very simple here. You just say, okay, fine, I want to bring this one down. We have an exponent, we have a base, and we have a number. So now I want to have b times x, which is an exponent, is equal to log the base, which is a, times the number, which is x to the power b. what was our x in the beginning? So we have b. Our x was log a x. So this is our x, it was log a x. So this one is equal to log a x to the power b. So we have proved the third one. Right. Now I want us to go for the last one, and then we can call it a day. So we have this one. The last one was saying log a, and then you have of x is the same as log b x, and then you have log b a. If you have noticed in all these problems when we're trying to prove these things, we keep saying let x equal to that, let x equal to that, let y equal to that, and then let x equal to that, let y equal to that. This is not an exception. We're gonna do the same thing here. So what we do here, we're just gonna say this is our proof, and then just let this thing, the numerator there, you just let x is equal to log b x, and because we have a and b here, you can use the same y. I think it's not gonna be a problem. We're gonna have y is gonna be equal to log b a. Now what we are going to do here, we're gonna use the same things that we're doing, saying that if I have a number equal to a base raised to an exponent, right, this is equivalent to saying that I have an exponent equal to a base, exponent equal to log base and number. So this thing and that thing is the same thing, but in different representation. Now what we will do here, we will try and change this and that. Let's start by changing this thing over here. So I am going to say that this implies that okay, it's fine. Let me just change these two things. So this one implies that this one, remember, what am I doing here? This one, this is the base. This one, because this one is written in this format, so whatever is this side is an exponent, and whatever is here is supposed to be a number. So we're gonna have our x is equal to the base is b, and we're gonna have an exponent which is x. And we have, in this case here, we have an exponent, we have a base, and we have an a. So we're gonna have an a is equal to b, which is the base, raised to capital letter y. Now if you look into this side here, we're trying to get up to here, so we don't have any b this side, so we want to eliminate this b. So what we will do, we'll solve for b in this equation and then substitute into that equation. That's what we will actually do now. So I can just say that a is equal to b to the power y implies that, remember that I wanted to solve for b. So in other words, I want to remove that. So what I will do, I'll just say a raised to 1 over y is equal to b to the exponent y raised to 1 over y. That's what we will actually do in this particular case. And if you look into this thing carefully, this y and that y will cancel out, and now this implies that a to the exponent y 1 over y is just equal to b. So we have our b now. So we take this b, we substitute it here. So we're gonna have our x is equal to, instead of b, I'm gonna write a to the exponent 1 over y all over x. this whole thing to the power x. Now, the power of the power, you just multiply the exponent. So this is the same as a to the exponent x divided by a y. So we're actually saying that we have x is equal to a x divided by capital letter y. So we have this nice thing there. This is an exponent, this is the base, this is the number, and then we use that conversion to that conversion there. So basically, using this conversion, we are going to have x divided by y is equal to log, what is the base here is a, and what is the number is x. And you go back and ask yourself, x was this and y was that. So which means that our log ax, which is just equal to x over y, is equal to x was log b, x divided by y was log b a. Therefore, we are done. Log ax is equal to log b x divided by log b a. So in most cases, when you're trying to simplify the logarithmic functions, you end up using these laws. That's all there is to it. I want you to know the domain. I want you to know the range. I want you to know, is it even, is it odd, and all those nice things, and how to prove these things. That's all that we have done for this particular lesson. And I would like to thank you for everyone for actually watching this, because we had an unfortunate day today, and hopefully things will go back to normal as time goes by. So thank you.